international conference even in this time of pandemic. I heartily welcome our Vice Chancellor Ma'am, Professor Annapurna Nautiyal Ma'am, our HOD, Professor T.C. Upadhyay Sir, our Coordinator, Professor S.C. Bhatt Sir, our Organizing Secretary, Dr. Manish Unyal Sir, Dean of School of Sciences, Professor R.C. Dimri Sir, the convener of this conference, Professor Suresh Nautiyal Sir, Director of USERC, Professor Anita Rawat Ma'am, our Chairman, Dr. K.S. Bartwal Sir, Professor R.C. Ramula Sir, and Prof.Sib Krishna Ghoshal Sir, and also I welcome all the invited dignities, delegates, and my dear friends. Now we will look forward to get an exposure about what the best of the brains think about this very dynamic issue of material science and its applications. Now let's move towards today's schedule. Today we will have our second session and third session for this conference. In the second session, there will be two keynote address. The first one by Professor Sid Krishna Ghoshal sir from UTI Physics Department, Malaysia, and the second one by Professor Mahavir Singh sir from Himachal Pradesh University. In the third session, there will be two invited talks. The first one by Dr. Kunjan Purohit ma'am, AVPG College, Dehradun, and the second invited talk by Dr. Deepak Joshi sir from IIT Delhi. And also there will be three oral presentations. The first one by Dr. Shubhendu Shekhar Khali, Physics Department PDF Fellow, IOP Bhubaneswar. Second one by Dr. Gaurav Karnatak, Soban Singh Jina University, Almora, Uttarakhand. The third one by Neelam Rani from Department of Physics Material Science Lab, Chaudhary Devi Lal University, Srinagar. Hereby, I will request Dr. K.S. Bartwal sir to kindly chair the session. Dr. K.S. Bartwal sir.
Thank you so much. First of all, I welcome all for this first session of the day. And this is the real business starting now. And we have two speakers in this session today, Professor Ghoshal and Professor Mahavir Singh. First is Professor Ghoshal. I welcome you, sir, for this first talk of the day. This is the keynote address 2. Little bit small, brief introduction of Professor Ghoshal, let me say. Presently, he is Associate Professor of Physics at University of Technology in Malaysia and working since 2010 there. Professor Ghoshal did his master's from Presidency University, Kolkata, and he did his PhD in physics from Jawaharlal Nehru University, New Delhi. He has been teaching for last 3 decades, and apart from the teaching, he has been working as a researcher in different areas of physics, and he has nearly 600 research publications, international and national and all, plus book chapters and books to his credit. It is a huge number. It is a huge number, sir. And mostly his research area are advanced optical materials, condensed matter physics, nanomaterials, and laser physics. So these are the vast areas in different field of physics, and particularly when we talk about the material science, about this conference. So he has all these areas, they well fall into the this material science, the condensed matter physics and the nanomaterials and all that. So may I now request Professor Ghoshal to please deliver his talk. Professor Ghoshal, please.
Thanks for your kind introduction, and I am grateful to the organizer for this opportunity, and I always look for this kind of thing in India. Wherever they invite, I just go ahead, because this is really a good contribution to our society and we must do it as Indian. So thank you so much. Let me just start and share the screen.
Full screen, please.
Yeah, I am doing it. Let me just do it again.
Either full screen or a bookmark, book reading. The
Is
second
it,
one.
now
Second
this is full screen. Is it okay?
No, this is not exactly full screen. Either you go to the book reading mode.
Yeah, that I know. Let me just.
Left to that. One
Yeah.
left.
Let me just do it.
One left. Right. This one.
This one.
This one. Click that. Right.
Yeah. Usually this.
Okay.
It's okay. It's okay now.
Okay. Okay. Please go ahead.
Thank you so much. So I'm really, it's my pleasure to be here today with so much of high-profile people and things. It's always a pleasure to interact with different people to get more knowledge. So what I have decided to talk on this problem, what we have been looking at for last almost 10 years, 10 to 12 years, is some of the rare earth doped materials, of course, man-made material, and how we can use the phenomena of plasmonics into this system to get better devices. So we have industrial linkage, we have the commercialization in the university. So with all this, we are basically trying to produce some miniaturized lasers and white LED, cool white LED, using some unique materials. And one of that material is basically the glass ceramic material doped with metal nanoparticle as well as rare earth material. So this work has been done with our ongoing project. It's with the Taiba University, where I have 2 PhD students, and also with UTM. And this we started 4 or 5 years before, and the actual project we started about 12 years before, and we were the first to start this kind of work in the world, and now it's really escalating into a different dimension, and that you are going to see as we go through this lecture. So let me tell you what are the main challenges in this field. So main challenges is that, can we produce rare earth iron doped glass, ceramic, or glass ceramic materials? Those are suitable not only for miniaturization of the devices, but for making laser, display, and LED application, especially cool white LED. So why we need LED? Because we have semiconductors and so on. For example, zinc oxide, gallium arsenide, indium phosphide, various other wide bandgap and intermediate bandgap semiconductors are already in the market. But there is a problem. The problem with this material, existing material, is that the affordability, because those materials are expensive, particularly the processing and the purification is very expensive. And that's why if you look at the LED prices are not getting down that much with last 5 years. Then other problem is the affordability, availability, because these materials are not also plenty on earth. So therefore, some of the countries who are having in their minerals and rocks or wherever, they are making the price high every day. As a result, we are in trouble. Then reliability. Of course, these semiconducting material devices are having a stability problem and durability problem, which are really the major challenge scientists are trying to resolve. And then environmental responsibility. That means when we manufacture any material, we start with any new material, whether man-made or natural, we have to really look at these 4 aspects. And that's where the application of the material is. So in this talk, I am basically going to give some idea about the rare earth. Many people knows it, but in different ways. But however, I am going to highlight their importance. And then we'll be talking about how this rare earth material, our focus is on holmium, which is a very good red, blue, and infrared emitter, because nowadays there is a tremendous research on getting the infrared, lower infrared and higher infrared laser, because infrared laser and deep UV laser has not been developed yet. In the visible region, we have a lot of lasers, but deep UV laser between 10 to 100 nanometer wavelength, and also the infrared laser between 10,000 to 15,000 nanometer wavelength is really a big issue now. Then we will be talking about the particular type of host. We are working on zinc sulfur borophosphate glass ceramics. This is not glass, this is not ceramic, this is glass ceramic. That's where the difficulty is, how to tune the crystallinity and the amorphicity together to get the light emitting property. Then I will be highlighting what new we achieved or what we are trying to innovate, and some of the results and discussions. I will not go into very deep technicality of the problem, because last 15 years I have spent on this, and really we got something like 200 to 300 high-class publications. But that's not the end of the story. Every time we do something, it opens up new avenues, and that I am going to discuss through the results and some of the interesting discussion, which might be helpful for the newcomers into this field. Let me just quickly remind you, there are 17 rare earth metals make all possible high technology gadgets in our life. For example, we do not have the color mobile phone, color television, any devices we talk about today, petroleum industry, then automobile industry, artificial intelligence, any sector we touch, not only electronics, with other sectors, wherever this online, for example, camera, devices, servers, everything is basically rely on the rare earth material. And one of the interesting thing of this rare earth material, this was 2010, this report came. Whole world, if we consider the whole world petrol reserve, entire world petrol reserve and the equivalent money, and only the rare earth, that reserve in China, that equivalent money is same. So it means that China is occupying 90% of the world reserve of the rare earth, and that's why day by day this price is increasing. And if we look at few grams of rare earth in 2000, the price was nearly few thousand rupees. Now it is 10 times more than. That means within 10 years, the price has gone 10 to 15 times higher. So this is really a challenge of, in both ways, that how we can minimize the use of rare earth, how we can recycle the rare earth, or how we can properly use the rare earth to get the better action or better effect into the devices. So in short, we do not have any color display without rare earth, and you can see the gamut of application and gamut of research in this rare earth material when they are put in different kind of other host, because rare earth itself cannot do, so they need some host. Like the COVID virus, they cannot do themselves, albeit they cannot open up their machinery until it finds a host. For example, human is the best host for them to replicate or to whatever do all kind of nasty job. Same way, the rare earth material needs some kind of host. This host can be glass, this host can be crystal. For example, we know ND laser, where EAG crystal is doped with neodymium, and that gives the ND laser, ruby, for example. So this is the way these rare earth materials are doped into different kinds. Why these rare earth materials are so interesting and so unique? Because they have the magnetic, catalytic, and phosphorescent properties, which are completely different from other materials in the periodic table, and they form the lanthanide series, where the electronic configuration, they have a xenon core and 4f electron. And as we know in physics or in material science or in chemistry, 4f and 4d electrons, 4 or 5d electrons are the so-called the nasty electrons. They give rise to all kind of functional material properties, including superconductors and all this kind of stuff. And they are really very, very difficult to understand. And these kind of rare earth material, they have 14 electrons in the 4f cell, and the transition among these cells, among these energy levels, give rise to all such complicated effects. So if we invest our whole lifetime only on rare earth, it will not be enough to understand them. They are very, very interesting material. Why they are interesting? There are reasons. So fundamental physics is very important. So they have the center field effect, they have the Coulomb field effect, they have spin orbit interaction, they have also crystal field interaction. So as a result, they show stark level splitting, they show various kind of spectral properties which are quite interesting to understand, which are quite interesting to exploit for practical application. And that's what people in the entire world are trying to do. So when rare earth, as I told you before, that these rare earth materials must be doped inside some kind of host. So what are these hosts? These hosts can be glass. Glass, what type of glass? It can be silicate glass like window glass or the glass. It can be lime glass. It can be like our Sprite or Pepsi or Coca-Cola bottle or paracetamol bottle. It can be telluride glass, it can be germanate glass, it can be phosphate glass. So human has developed a lot of kind of inorganic and organic glasses. Wherever you dope this rare earth material shows newer and newer kind of effect, interesting effect, and that people are trying to understand, and we are also trying to understand them. So Japan is called these rare earth as the seeds of technology. So without this, technology is not possible. For example, now you know in a new series of Toyota Pyrus car, they need 5 pounds of lanthanides for the hybrid system to run the battery for 10 to 15 years lifetime. So this is very interesting. All the iPhones, all Samsung phone, everything, they have very high amount of rare earth materials used for making the color display and other kind of effect. And US Department in the defense, they use a lot of rare earth material. US Department of Energy, they call them as technology material. So this is the importance of the rare earth material. So why we choose glass ceramic for doping this rare earth material, so-called holmium? There are many reasons. So laser glass is 5 times cheaper. Of course, I told you affordability is the most important thing, okay, in any kind of science. What complex science you do does not matter, but the affordable, when it goes to the common public, when it goes to the common people, they will ask, what is the price? They don't care how the research has taken place, in which laboratory is involved, what is the complexity of the research. They will just ask, if it is the price is okay, we can pay. And also, second question would come, longevity, because if that failures, then they will not buy that. So longevity is the next issue. Environmental responsibility, of course, for the politicians, for the management people, and for the intellectual people, this is important. But for common people, really do not have sense. They just use and throw, like the way plastic. Plastic is so handy, so easy to use. People don't really care about the environment, but we must care as a scientist and as an intellectual or as an educated people. So that's where the environmental responsibility will come. So glass ceramic, we can give any kind of shape, molding. They are transparent. Transparent means maximum light will come out of the material. When emitter is sitting inside the material, they are stable, they are suitable for lasing. So these are some of the very interesting reasons. And that's why Livermore National Laboratory, American Defense, they are producing this kind of phosphate telluride glass at large scale for almost all the defense and other display devices in the technology. So another reason why we use these glass ceramics, the benefits comes from other reason. They are partial crystalline, so the crystallinity play a role. Remember one thing, the rare earth will not show any effect. It chooses the particular host and it shows different effect. Why the host is important? Because depending on the symmetry and asymmetry of the local environment, local structure of the host, of the crystal or the ceramic or the glass, the effect of rare earth would be entirely different. That means the light emitting property, the magnetic property, the properties of the rare earth, the stark splitting, all this kind of thing, Yantel distortion, all this kind of effect in the rare earth material would be completely different depending on the surrounding symmetry or asymmetry of the matrix or asymmetry of the network. And that's what it is challenging. That's what the tunability actually comes from there. And material science become harder and harder when we work on them. It's not easy. And that's where the quantum simulations and large-scale simulation people need to perform to match the experimental result, so that if it can predict something more, it would be beneficial. Then the complex theory comes, like judo field theory, other theories come in the picture to predict the light emitting property or lasing properties or cool white LED properties of this material. So that's the way it goes. So of course, the glass and things are low cost. That is another reason. So they have great optical properties, and you can give any kind of shape, and also you can make very large seat. That means you can make something like 42 or 64-inch television, or you can put in the entire wall of the skyscraper building, so that in the public places, on the roadside or in the corner of the city, people can see. So we have already in New York, in the Broadway Road and Times Square, we have big screen. In Japan, or if you visit in any countries, those who have visited, you must have seen them. So these large screen can be created by this kind of material. So that's the interesting part. So why we choose holmium suddenly from 17 rare earth? We have been working on all actually. We have explored something like already 15 kind of rare earth. But in this lecture, I'm going to only present holmium, because we recently noticed that holmium can be a very good agent for green, red, and some infrared emission. That's the but with the present holmium only, with the present glass and ceramic, there is a problem. The problem is intense visible emission is okay, but non-radiative transition is too high. Because if the non-radiative transition is high, means phonon will eat the photon. So as a result, phonons are the enemy of the photons. So photons from the material will not come out. How we can eliminate the effects of phonon, which is responsible for the non-radiative radiative decay? That is one of the challenge in these materials. What are the limitations? So limitations is basically the quenching and small emission cross section. So intensity quenches because of the non-radiative transition, and also the emission cross section of the rare earth is already low, and that's what the improvement is needed. How we can improve them? We can put a lot of different kind of metallic nanoparticle, but in the metallic nanoparticle, silver and gold are the best. Silver has the surface plasmon resonance. So when we put this kind of nanoparticle inside the glass ceramic and then bring the rare earth in front of them, interesting thing happens. So plasmon mediated effect happens. So this plasmon mediated effect can push the absorption and emission cross section of the rare earth very high. So then we are going to see some enhancement or increase in the optical radiative properties. That means the stimulated emission cross section would be getting enhanced. That means we'll get very high or intense photon emission from the material, and that's where our demand is. That's where the industrial demand is. That's where the application is. That we are basically looking at. What is the speciality of the zinc borophosphate glass, why not tellurite, why not silicate, why not germanate, why not tungstenate? Okay, every glass is having its own benefit, but phosphate glass is already demonstrated by American Navy, American Defense, and it is on use in the medical sectors and so on, but it is used for the high UV emitting and for also strong visible emission. We need for some different other wavelength, and we also would like to miniaturize those devices. Eye-safe emission. Eye-safe emission is one of the very important things, so that this laser should not damage the eye retina or the cornea. So this is basically the idea of it. So borate has high thermal stability, low melting point, and high transparency. That's why we choose borate. Phosphate we choose because it has low photon, low glass transition temperature, and large intake of. It can take a lot of rare earth concentrations. So zinc we use to stabilize chemically the network or the glass ceramic structure, and sulfate we use basically to improve the intake of rare earth. So this is already a nice kitchen chemistry. So we cook up all this material to get a good functional material. So that's why we call this glass as functional glass, because in this functional glass we entirely change the local potential. So for the glass, potential is already corrugated, and if you look at the free energy landscape, quite complicated. That's why the glass is sometimes called supercool liquid or complex fluid. Even if we put some crystallites into this, it becomes more complex, the potential landscape, and this potential landscape controlling is really a difficulty. And if you look at Walter Cohn paper, which is called nearsightedness effect, here we bring such kind of effect in the potential well in the mixture of crystallinity and amorphous, and tune the property of light emission. And that's where the complex and functional goal of material science starts. So what we would like to do? So most of the earlier reports or research is going on. Many are doing. It's not we only doing. So a lot of groups in the world are doing. But most of the people are looking at the optical properties and structural properties. We go one step ahead. We want to make a correlation. We want to determine a correlation between structure and dielectric properties, because dielectric properties of this material play a very, very important role. Why? Because polaron, bipolaron physics into this kind of material become very important. How to control the polaron and bipolaron physics, that's another new domain of modern research. Theoretically, people are trying to understand, even in superconductor, in semiconductor, in this kind of material, because they are also having a little semiconducting properties. So we would like to know them. So determining the structural and dielectric correlation, dielectric and optical correlation in this material is very important, and that's what we looked for. So here is the complex landscape of our study. We prepare some of these kind of glass ceramics. Then we characterize in all possible ways, not only want to characterize. Remember, our aim is not just to publish the paper. We want to develop a prototype, then we go for device manufacturing, and if it is successful, then the industry can put more money, and that we are trying to do. So we go through all kind of characterization possible in the laboratory. We have something like 20 to 30 different kind of characterization into this material. Then we have also having a theoretical group, simulation group. So they also supply some of the simulation data to fit with the model calculation, with the experimental result, and then we go for something new. So here is basically the landscape. This is basically the structural network of this material. As we told, that we put holmium into the phosphate borophosphate glasses, zinc borophosphate glasses. Then we bring the silver nanoparticle and then see the impact of both into this material. And this is the surface plasma resonance ring of the silver. And as you can see in this diagram, that the emission cross-section of rare earth is already very low, and how we can increase the emission cross-section of rare earth, that is the most important challenging aspect into this research. So I will not go through the much of the much of the literatures and reviews you can see. But what I am trying to tell you, if you look from 2010 to 2021, nearly few thousand classic paper, all high impact Q1 paper. I'm not talking about Scoopus, I'm not talking about Proceeding, I'm not talking about non-index journal, not Q2, not Q3, only high impact publication. If you look at American Physical Society, European Physical Society, Elsevier, and so on, you will see this number is quite large, and every time new reports are coming. So this is the indication that this field is opening up, and people found some promise into this area of nanoparticle and rare earth synergy. I call it synergy. Some of the paper we have written for the rare earth and nanoparticle synergy, how it is going to change our future devices. Not only light emitting devices, also self-cleaning glass. For example, maybe next time I'll give another lecture in the skyscraper building like Burj Khalifa Tower. It is very difficult to clean the window after a dust storm because those buildings are in the midst of the desert. So self-cleaning. Those car, expensive car, every day or every week, celebrity cannot go to clean them. So once you buy the car, maybe in 5 years you have to clean once, Rolls-Royce car or Bugatti Veyron car or whatever, the new series of car. So how to protect them from the dust and so on? Those who go for hiking, those who are in the deep ocean, taking the pictures in the National Geographic camera lens, the spec, the player are playing in the field, in the dusty field, so they are Ray-Ban glasses and so on. How to keep them protected from the glass? So again, the silver nanoparticle, titanium nanoparticle plays the role. Those are already in the different areas of functional materials or smart material research that we are already doing. So functional and smart material is another new domain of material science. All right. So what is the what is the synergy between the nanoparticle and the rare earth? So in one side, holmium is a rare earth which are having strong absorption cross section or absorption peak in the region of 450, which is visible. And on the other side, you have the silver nanoparticle, which has strong surface plasmon absorption band around 450. That's good news. In fact, nature gives something, but it hides from human something. We human need to explore those things to beat the nature to get those things. And if we can bring this silver nanoparticle in front of the holmium, because of the overlying of the wavelength, it would be possibly a good thing that some of the photons would be absorbed by the rare earth, vice versa. Some of the photon can also be absorbed by the nanoparticle, but the probability of absorbing the photon by holmium from the silver nanoparticle is so high, so we would be in the win-win situation. That's exactly going to happen as we see in the next few slides. So if we look at the mechanism of rare earth photon emission and nanoparticle photon emission synergy, and how this nanoparticle is going to feed the rare earth so that rare earth will take more photon from these nanoparticle, so there will be more transition. When they fall back to the ground state, emission would be very high. So we are looking for strong emission cross-section or stimulated emission cross-section from the rare earth, and that basically the idea, that basically the issue we are talking about. So I picturized this in some paper. First time I picturized this effect in the following way. Suppose you are taking the shower near a swimming pool, you open the tap before getting into the swimming pool, you want to wash yourself and you open the shower. Now that time, suppose heavy rain starts, so the shower on you without the rainfall is something like laser is falling on the holmium. So holmium is like you and the shower is like laser photon. In any experiment, of course, we have to trigger, we have to induce the transition within the rare earth by some kind of laser. So this is the laser pump, which is last hour, and U is like the holmium. Now suppose you were cleaning yourself, suddenly heavy rain started. So definitely this heavy rain would be absorbed by your body, so your body will immediately go more cool and cool, because the surface area, each unit surface area without the rain cloud, suppose 50 water droplet was hitting per second from the shower, now 5,000 would be hitting per unit area on your body skin due to the heavy rain. So therefore, the rain is acting like nanoparticle surface plasmon field on the rare earth. So this is called the synergy. And if we can tune this synergy, if we can control this synergy, how we can control this synergy? We have to choose the right composition of the glass ceramic. Remember, the moment you form the crystal lattice or the amorphous material, they have a lot of bonds, so they have a lot of molecular phonon. This molecular phonon will eat the photon faster than the holmium. So how to tune that complex game? So this molecular phonon is like heavy wind. So at the same time, if heavy wind starts, then most of the rain particles will go away from your body. So instead, your body would be less wet than if the wind was not there. So the windy situation, stormy situation is like the situation of phonons in the solid. So the complex material science is here. Material science is not that easy if you look at, because the potential field in the glass and ceramic in the presence of nanoparticles and so on is very poorly understood, because nanoparticle itself is poorly understood. Rare earth also poorly understood. And when you bring glass, crystal, rare earth and nanoparticle, which is a very complex business, and that's where we are looking for. Okay, so these are some of the research again on different kind of glasses, but as I told you, because phosphate glasses is more promising for various application reasons, so that's why we are working on. So I have many students, something like 30-40 PhD and postdoc student. Various students is working on, some are working on cool white LED, some are working on laser, some are working on display devices, and that's the way a group is working here in the research field. Okay. So what do? We therefore synthesize some of the glass ceramic, then we characterize them, then you evaluate their potential for lasing action. But if the lasing action or the light emitting action is very, very promising, then we look for the purity of the color emission. Suppose some material emit the light, but we do not know which purity of the color. So purity of the color is also extremely important from the application point of view, and that's what we are trying to do. So what are the characterization we do on this kind of? We do the absorption, ultraviolet, visible, near infrared absorption spectroscopy and photoluminescence spectroscopy, because this is needed for optical characterization. Then we do impedance spectroscopy for most of the dielectric measurement. Then we measure the density. Of course, density is important to calculate any properties of the material. Then we have to do a lot of structural and morphology characterization, such as XRD, X-ray photoelectron spectroscopy, XPS, Raman spectroscopy, FTIR, Fourier transform infrared spectroscopy, Raman spectroscopy. Then we have to also do TEM, transmission electron microscopy, high resolution transmission electron microscopy, FESCM. So all these things for the morphology characterization. So the complete characterization result of structural, morphological, impedance, or dielectric properties, optical properties, then monochromaticity properties by the CIE, Eclairage diagram. We have to do all this to understand the properties. I'll quickly go through the technicality of the experiment. If some of you are in the audience are interested to come after COVID, maybe We can help you to come here to do some research for 2-3 weeks program. There are a lot of programs. Indian government like DST and UGC give those money. Some student has already come here from India, so they have spent some time and go. So you can also try explore those possibilities and can expose or extend your research or even if you want to share your research with us to give us some important and new knowledge, you are also most welcome in sabbatical and so on. So that's the purpose of this webinar, not just to tell you science, what is the future possibility of research collaboration. That's also very, very important. So this is basically the kind of what I would say that all food items in one dish. So here I have explained how we start from the raw material, then put in the furnace, grind them, melt them, weigh them, and then in the furnace we put in the porcelain, in the platinum, in the aluminum crucible to get the kind of material. This left hand side is showing the material without rare earth doping, right hand side is showing the material with rare earth doping. That's why the color change, and this is the way we get. So heating and cooling schedule, that means at what temperature we heat, shock heat, then we quickly quench, that means very fast we cool down, then again slowly heat, then anneal, then we cool finally to room temperature. This temperature schedule is very, very important to get the right crystallinity. Maybe we want 25% crystallinity. Some of you can tell, no, not 25, 18% crystallinity, rest is amorphicity glass. So this tunability of the glass and crystallization requires very complex temperature scheduling, which is called cooling heating effect, and that we are trying to do. So this is the kind of glass we get. X here is indicating the concentration of the holmium. Remember, the holmium is the most important guy, rare earth, which will emit light. So our target is on rare earth material holmium. Then how to tune it? Rest of the thing will come. The structure, the composition, then how to feed it, because its photon intake is low. Photon intake means the absorption cross section is low. As a result, emission cross section is low. How to feed it more? That's where it will come. It's like child. A child does not get feeded well by the mother because mother is also working outside. So what to do? You keep a good maid or bring some relative who can look after the child all the time and feed more. So the feed more to the child means growth is more, the baby would be healthy. So holmium is like an unhealthy baby because its absorption cross section is low. How to make it healthy? So bring the silver or any kind of metallic nanoparticle who can give a lot of surface plasma and photon into it. As a result, holmium would be well feeded. As a result, holmium would be well vomiting. Vomiting means it would be emitting. So absorption and emission cross section would be high. So we will achieve the target that we want. So we prepare basically 3 series of material, glass ceramic material in this composition: borate, zinc sulfate, and holmium oxide and phosphorus oxide with the right weight, 40, 30, 30. This is called the nominal composition in mole percent, doesn't matter. So one series is with only holmium. Second series, we choose the optimum concentration. Then we dope silver chloride. Silver chloride is cheaper than silver nanoparticle. So either we can buy silver chloride or we can buy silver nanoparticle. If we put silver chloride, heat it in the material, then through a process called the coalescence and rippling, it will form the nanoparticle. But if we already buy from Sigma and Rich or from company Merit, high quality silver nanoparticle, we can also dope that. Then we can heat it up so that some of the nanoparticle, bigger nanoparticle, would be decomposed into smaller. So we started with both. In one hand, we let the system to form the nanoparticle. On the other hand, we buy the nanoparticle and forcefully dope in the system. We wanted to see which produce the better effect. That's what the 3 series of glasses. So here are the 3 series of glasses, their properties. So we have noticed that if this does not contain any rare earth, contain any nanoparticle, only rare earth, density increases. Then the second series, contains silver nanoparticle, then silver nanochloride to silver nanoparticle, also decreasing density, and again if we put the pure nanoparticle, again increasing density. So this clearly indicates that the glass ceramic properties are changing whether we are playing with pure nanoparticle or silver chloride. So that's the most important thing. So how this happens? So there are mechanisms. The mechanism is called the redox reaction, reduction oxidation reactions in chemistry. Basically, chlorine has 1 electron, silver is positively charged, so this electron is captured by the silver form the neutral atom. Many neutral atoms join together to form the silver cluster, and this silver cluster we call nanoparticle. But if we start with already pure nanoparticle from the company, again some of the bigger nanoparticle can form the pure or nanoparticle into smaller sizes. So basically the idea is to tune the nanoparticle size, that's it, because the surface plasmon property of nanoparticle is dependent on the size and morphology. If we can tune them by heat and cool control, cooling control, temperature control, we can get whatever we want. So this is the process by which this nanoparticle form, called Oswald ripening and coalescence. This you can. So how do we know that this is really the ceramic? That means in the background of amorphous, there are crystallites. Something like this. Suppose you are in the middle of the ocean, then you suddenly see there is a small island, or there is a big rock like Partharsarathi rock in Kanyakumari. So those rocks are like crystallites in the background of water. So everywhere water, suddenly a small island, Andaman Island, which is something like, or Maldives or Mauritius. So they are something like the crystalline island in the midst of Indian Ocean. So here our Indian Ocean is like glass, Maldives, our other islands, Andaman Nicobar, Mauritius, these are something like crystallites. So that's why the amorphous and crystallite together is called glass ceramic. So this we produce. So how do we know? We look at some of the chunk in the material through the HEMVATI study. Then we look at their crystalline. This is called lattice fringe profile through the SAED or FFT, inverse Fourier, first Fourier transform, or you can do SAED, selected angle electron diffraction. From there you can find the lattice parameter. And these lattice parameter, when you check with the JCPDS card number, then you see this is corresponding to the borate crystals, and that's clearly indicated that we really formed it. So Singh is believing, so this is the proof that we are working on glass crystal, glass ceramic, not just glass. Well, how do we know nanoparticles are formed? Then we take every glass ceramic from this, then we do TM and also HRTM, again measure the SAED, first Fourier transform, then we see again very nice lattice fringes are formed, and that's what we are getting the nanoparticle. So it is ensured that the nanoparticles and crystallites are there. Now we look for the nanoparticles, another proof that does this nanoparticle is really emitting the surface plasmon? Yes, we look at the absorption peak and we look at surface plasmon resonant absorption. Depending on the size, they give two peaks. One peak is around 442, another peak is shifted around 445, 452. So this is like bigger nanoparticles at smaller wavelength and smaller nanoparticles at larger wavelength. So we are within the 450 regime, and we know that rare earth holmium is also having the emission in 450D. That means there is an overlap, and that we are going to make a synergy, and that's what our interest is. How do we know? Another proof that this material is glass and crystallite together. That means in the background of the glass, majority is glass, but there are little crystallites in the material. So we have seen that there are sharp peak in the X-ray diffraction. We'll also do Raman, we'll also do XPS to prove further, because only one investigation will not be enough, because you have to cross correlate, you have to bring other evidences, cross evidences to re-verify, reaffirm that this is really true. So these are basically the X-ray data. Then we go to the Raman measurement. In the Raman, we also see the same peak, and we confirm that these crystallites have formed. Then we analyze the Raman peak more and more to see where is the phosphate, where is the borate, because borate and phosphate are very interesting material. They can form different kind of units, PO2, PO3, PO4. Similarly, borate, BO2, BO3, BO4. But remember, BO4 and PO4, that means phosphate in 4 and boron in 4 are the most stable units. We also want that, because I told you stability of the device is an issue. Stability of the white LED and laser is an issue. When you put in the miniaturized toy of children or in the PSM game module, so this laser, miniaturized laser, stability is very important, because constant heating would be going on. So in the PlayStation and so on. So that's very, very important. And that's why Raman spectral give the information about the crystallinity, about those kind of unit stable formation. How do we check? We call something called N4 ratio. N4 ratio means to show that PO4 units are more in the system, BO4 units are more in the system than other units. And that clearly indicates that yes, indeed, they are there. So we are making the glass ceramics which are highly stable. So this one issue is solved. The second issue, whether we have formed the right structure, or is there any impurity, is there any bad elements in the structure? No. Go for FTIR analysis, look at the spectral weight, and from those weight, we can clearly find the concentration of those units, and then we confirm that they are there in the system. Then we could do the impedance spectroscopy to look at the source of polaron or bipolaron physics. Then we look at the impedance, resistance, and also the dielectric constant, complex dielectric constant, because complex dielectric constant is related to the refractive index of the material. So refractive index we measure, refractive index we calculate from the Lorentz and Sellmeier formula, Dimitrov-Sakar relationship. Then we also calculate the refractive index from the dielectric constant, from the dielectric measurement. We want to match, we want to cross-relate, and then compare with the experiment. So from all such data, we see that they are really correlated. Then we look at the structural symmetry. After looking at the structural dielectric correlation, then we go for the optical studies. Because remember, main aim is to do the optical properties, but optical properties depend on the structural symmetry. So first we look at the absorption in all three series, and we see that as we are doping the nanoparticles in the system together with the rare earth, the absorption is becoming more cleaner, and the absorption is really getting high. And some of the new absorption peaks, which were weaker without nanoparticle, they become stronger with nanoparticle. So we are therefore in the right track. So from there, we calculate the optical band gap. Optical band gap is extremely important quantity for solar cell, for solar concentrator, for display devices, for many other devices. As you know, the game of semiconductor physics or laser or solid state laser is to do with the disorder, which is called Arbach-Tell, is to do with the band gap energy. Band gap energy is the most important thing. If you have narrow band gap, you have some application. If you have wide band gap, you have some application. If you have intermediate band gap, you have some application. But if you have wide tunability of the band gap, then you have all application. And that's where glass ceramics are interesting, because you can tune the band gap over a wide region by controlling the concentration of the nanoparticles and combinations. And you can put 2 different nanoparticles, 3 different nanoparticles, 2 different rare earth, 3 different rare earth, depending on your aim. So that's the way we are trying to do. So when you put the silver nanoparticle, in the presence of silver nanoparticle, the disorder changes. That's what exactly I was talking about. Local symmetry of system changes. This local symmetry will control the optical properties, and that's where judo field theory comes in, and we also do judo field theory to compare with the result to get them. Then we look for the photoluminescence, which is the emission spectroscopy. And we see intense red and green emissions. So these materials are really suitable for red and green laser fabrication. And for the first time, you can see the literature and check. For the first time, we show that we can get very high branching ratio and stimulated emission cross-section in this material, and that's why our aim is fulfilled. So stimulated emission cross-section and the branching ratio of this material is very high, and that's what we wanted to achieve, and this is the right material for fabricating the laser. But the last thing we want to check, what is the purity of this color? So we have wide green, because we know in the visible spectrum, green can be several wavelengths. Red can be several wavelengths. Yellow can be several wavelengths. But which red wavelength? Which green wavelength? That means the monochromaticity and color purity can be only checked by the chromaticity diagram. This is called CIE chromaticity diagram, and this is called the coordinate for the chromaticity. When we check, we see the color purity for red and green is quite interesting, and that's what we wanted, and we achieved the target for the time being. So what are the novelty of this work? The novelty is intense red-green PL, and also the purity in the color chromaticity, and the branching ratio and the stimulated emission cross-section is very high. For the first time, we showed that by tuning the structure and dielectric properties, you can tune the entire lasing property of the system. So in conclusion, I would like to say the new series of holmium activated zinc sulfur borophosphate glass ceramics we successfully prepared, embedded with silver nanoparticles. And structural optical dielectric correlation we have shown for the first time. And we demonstrated that this structural correlation is very helpful for making the devices and triggering the other optical properties in the system. It is called the synergy, and by controlling the synergy of the nanoparticles, which is basically, synergy means basically the creative combination of this innovative way of combining these different properties to create another new, called emerging trends in material science. That's why we call these materials as functional materials. Remember, these materials is not provided by nature. We have to synthesize in the laboratory. We have to customize or tailor them, and that's the way we can achieve new devices in the world. So the present work is beneficial for the development of efficient photonic devices and many other optical devices. So what is next? This is not the end of the story, rather this is the beginning of the story. We have achieved maybe 1%, 99% is remaining. So I call it, this is the dark area in this science. Material science is more than the lightened area. The lighting area is very small. Now the research has been started. It is in the infancy stage. The dark area is more, so we have to enter into those gray area and shed some light so that new physics, new concept is developed, new knowledge is generated, and that's the purpose of this webinar, to disseminate the new knowledge that we are trying to understand. So evaluation of the gold and titanium nanoparticle combination into this material we have started recently. More Judofold calculation is required with the magnetic and electric dipole effect that is not quite explored, and still today people do not know how to include the nanoparticles effect in the Judofold model. That is the theoretical model, and how to understand that is another. Then based on this material, we are trying to design some prototype, so that if the prototype is successful, and the COVID came in between, so as a result, most of the suppliers are not supplying material everywhere. The same problem. Country like India is better because we have a lot of development and supply, but here we mostly depend on the materials from outside world. So because of this custom clearance and so on taking time, so research is a little bit delayed because we have to depend on high quality material to get this kind of data. So I would like to acknowledge, of course, UTM for providing a lot of grants into this. Central facility, we have fantastic facility we call UPMU lab. In one lab, 40 to 60 different kind of high quality machines are sitting for characterization. We have wonderful laser laboratories. So ministry is giving money, university is giving money, and of course our faculty and head department is helping to get the research. And Taiba University is also helping by sending good students to do the research. Of course, I'm grateful to the organizing committee, particularly Manish Upyal, who has taken the initiative and contacted with me constantly. And thanks to you, particularly for your initiative. And you are really contributing together with the university and colleges in Srinagar and GARHWAL to disseminate the knowledge. That's where our role should be. We must disseminate the knowledge to the young generation so that the human dies spirit would work. That should be our idea in research. So thank you so much. I think I have completed in the right time, and some more questions or anything would be welcome. So thanks to the audience for listening my lecture and spending some time. So we are expecting some questions. And there is a say, the man who asks a question is a fool for a minute. The man who does not ask question is a fool for life. So it's your choice to ask or not. With that remark, I end my lecture. Thank you very, very much.
Thank you, Professor Ghoshal. And if there is any question from the audience or my colleague sitting there, please.
Hello, sir.
Yeah, please.
Sir, I am Vaibhav Chauhan from IIT BHU. I wanted to ask that how can we calculate Jude, Ophelt, these parameters? Is there a particular model for calculating?
Yes. See, Jude-Ophelt is a very celebrated model. If you asked me how to calculate, I would suggest you look at original 1964 Jude-Ophelt paper first, and then in a series of papers, something like in last 10 years, we have published, my student, about 120 Q1 paper only on Jude-Ophelt. You can download them and read some of them. In case you face any difficulty, you can write me an email. You can get my email from Dr. Manish, and you can send me. I will send you the entire calculation mechanism you do. So I would be very happy to do so. So please do that.
Okay, sir. Thank you.
Any other question from the audience or my colleague sitting over there? It seems there is no question, but I have a query, Professor Ghoshal.
Yeah, please.
I have been working a little bit on the visible phosphorus, and so in that case, if you want to enhance the persistence of that particular phosphor, what you used to do, we used to do co-doping in that. Co-doping in some cases, suppose in your case it is holmium, and then plus erbium, both are 3+3+. So in that case, we have found that yes, that persistence goes up, and decay time goes up. Okay, but in case of nanoparticles, we have not done it. Is it possible for you to do this nanoparticles as well as the co-doping of 2 rare earths, or sometimes 2 nanoparticles and 1 rare earth? Something. Have you tried it or?
Yeah. So we have also published paper only last 2 years. This is the new, and now we are actually writing 3 more paper on that. Exactly. Now in one we have put holmium, cerium, and lanthanum. In another we have put holmium, erbium, and ytterbium. Another we have put holmium, erbium, and europium with silver, gold. In another we put 3 rare earth, 2 nanoparticle. In one we put 2 rare earth, 3 nanoparticle. In another we put 3 rare earth, 2 nanoparticles. So these 3 papers is going to be in the series, and we have found in one of the combination the chromaticity point exactly reach at the center of white. That means cool white LED is possible, and I hope this should be our first paper.
That's very nice. Very nice. But at the same time, it will be really difficult to know which electron is taking part in that transition from second rare earth or first rare earth or the third rare earth. It will be difficult, though the result will be very good. You will
you are absolutely right. Now the question would be, theoretically, as this IIT BHU student was asking here, that theoretically how to predict whether it is a single transition or it is the combination of the transition. That means whenever there would be single transition, you know, the line would be broadened. How to control the WHM of this, that means, as you are saying, more sharpness of the line broadening we control, more persistent in the phosphorescence we can control. That would be another complex calculation, or I would say it's not the theoretical calculation, maybe some computer simulation. Unfortunately, we do not have much computer simulation for disorder system. Most of the computer simulation, like if you look at our Y2K or quantum express or whatever, they are mostly for the periodic lattice or periodic system. So for disordered system, the quantum simulation is not developed yet. But yes, there would be molecular dynamics or the calculation, something like density functional theory calculation or quantum Monte Carlo to predict all these properties. That also some of the students are working here. Thank you so much for reminding this. We will be looking at it more. Yes, you are right.
Yeah. I wish you all good luck in this. Thank you so much.
Sir.
It was very nice presentation and very informative also. And for our youngsters, it was really very good piece of work you have shown. Thank you so much. Once again, thank you.
Thank you. Thank you so much for your kind.
Okay, now you can just out of this. Okay, fine. Thank you. So, Manish, second speaker hai? Okay, now we have the second speaker. Singh Saab, Professor Singh has come.
Yes, yes. Morning, sir.
Okay. Good morning. Good morning. So, Professor Singh, welcome. Welcome to this seminar. And
Thank you.
Professor Mahavir Singh is from Himachal Pradesh University, Simla. And if you remember that 18-20 months back, we met in Srinagar.
Yeah.
Srinagar,
Yes.
that was very good meeting. And we met only in this seminar only there. So he's Professor of Physics at Himachal Pradesh University, Simla. He has done his master's from Himachal Pradesh University there only, and PhD from IIT Delhi. He has many recognition to his credit. Some of them I will list here. He has been the Vice Chancellor for IEC Himachal Pradesh during 2015 to 2018. He has guided successfully more than 20 PhD scholars, I think, so far. And he has a good number of publications, more than 150 refereed journal publications he has so far. And he has some book chapters and book also he has published. And presently he is working in magnetic materials and multiferrous materials, which is very fast growing field in this area. And particularly for the medical application, these magnetic materials, magnetic nanoparticles and nanomaterials are very, very important. So I request Professor Mahavir Singh to kindly deliver his talk. Professor.
Thank you, Dr. Saab. Thanks for giving me the opportunity. First of all, thanks to Dr. Manish and Dr. Nautiyal Saab and Professor Bhatt, Professor Upadhyay, then Professor Harbula Saab for giving me the opportunity. We know that we are passing with tough time in the pandemic, and my personal salute to all the organizer that they have took this challenge, this academic event. So my to organizing team. Today I am going to discuss about, as you know, when we talk about this COVID-19 coronavirus, so we talk about first wave, second wave, third wave, fourth wave and all. So similarly in nanoparticle, earlier speaker also talk about various kinds of nanoparticle, and I am also going to discuss with magnetic nanoparticle. So there we discuss about shape, size and surface. Shape, size and surface due to size, due to change in size. So basically virus also change different in different environment. That is why its behavior is different. Sometime it is single variant, sometime it is double variant, sometime it is even triple variant. So it is basically somewhere. So shape, size, and surface morphology. These three important, physical property are responsible for, changing the behavior of this coronavirus. So I am going to discuss these magnetic nanoparticle, the effect of shape, the effect of size, and effect of, surface. It may be magnetic property, it may be electric property, it may be other property also, whether it is optical, mechanical, or other optoelectric or optomagnetic, other kinds of property. But somewhere definitely we can correlate with the health sector, as chairperson already mentioned about the importance of these magnetic nanoparticle in health sector. So the topic of my today is significance of surface size and shape of magnetic nanoparticle for the future application in health, communication, storage, and water purification. So all the four factors are important. So basically, magnetic nanoparticle are unique in the sense its surface to volume ratio is maximum. Magnetic nanoparticle are unique in the sense they are eco-friendly, they are biodegradable, and they are biocompatible. Moreover, its surface to volume ratio is very, very large. That is why they are very, very effective for health sector, for communication sector, for storage sector, and for water purification. So in the present time, I think in the material science, people are talking about composite system or hybrid system. So when we talk about hybrid system in magnetic environment, so in magnetic system, we talk about hybrid system means at center we have a magnetic system. It is coated with some kind of graphene or reduced graphene oxide, and it is also somewhere coated with suitable kind of polymer. So basically, hybrid system is the future material in magnetic sector. So a hybrid system means one is polymer, other is graphene based product, and other is good magnetic system. So this hybrid system or this hybrid composite system will play the important role in future applications to come. Whether it is, RT-PCR detection. As you know, for COVID test, we need highly skilled manpower. That is why there is some kind of errors also. But for, detection of this RT-PCR, there are some chances of error also. But through magnetic, this hybrid system, we can detect this coronavirus, and there are few reports published in Nature and other important journals that there are various trials going on, so that we can have simple kind of testing as it is already in other detection purposes in health sector. So we need at the present time a simple test which can detect coronavirus easily, effectively, and at the same time we do not need any kind of skilled manpower. Simple person can detect also that. That is the beauty of this magnetic hybrid system. So basically, magnetic parameters, all these parameters we all are aware of. So basically, any kinds of magnetic system we have to control, whether it is initial permeability, saturation magnetization, corrosivity, electromagnetic medium. When we talk about electromagnetic medium, it is electric as well as magnetic. Then loss is also important. When we want to use magnetic material in communication sector, then loss is also very, very important. So these magnetic parameters are very, very useful for designing or engineering the materials for various kinds of application. So this magnetic system, we also talk about, one is hard magnetic system and other is soft magnetic system. So hard magnetic system means whose corrosivity is large, and soft magnetic system means whose corrosivity is low. So in some application, we require soft magnetic system, and some application we require hard magnetic system. Say for example, if we want to use in health sector, we need soft magnetic system, because in soft magnetic system we can achieve super paramagnetism, which is a unique kind of phenomena which exists at nano level. That is super paramagnetism is very, very unique, and for if we want to use in any kind of specific application in health sector, say for example treatment of cancer, or for treatment of targeted drug delivery, or for treatment of others kinds of genetic kind of genome sequences and all. So we need SPM kind of magnetic nanoparticle. So SPM is the prerequisite requirement for to use these magnetic nanoparticle in health sector. So we all know that magnetism, the cause of magnetism is domain. So, but that is ordinary magnetic material. So ordinary magnetic material, we say that it is made up of various kinds of domain. But when we talk about nanoparticle, magnetic nanoparticle, then it is not domains. We talk about single domain. Then even we talk further about SPM. So super para is basically even lower than the single domain. So SPM is a unique state where basically in the absence of magnetic field, there is no, magnetization. But once if there is small fluctuation, magnetic impurity, it can easily be detected. So if we have magnetic nanoparticle which have super paramagnetic kind of character, that is very, very effective sensor, for it can even detect minute magnetic impurity also. Till date, there is no such kind of sensor in especially for detection of magnetic impurity or detection of magnetic pulse. But definitely, if we have a magnetic nanoparticle having super paramagnetic kind of, no doubt it is challenge. It is difficult, task to achieve this SPM even at room temperature. So that is difficult. But anyhow, if you want to use for hyperthermia application or for targeted drug delivery, we have to achieve this. So definitely there are few groups who are fabricating excellent kind of magnetic nanoparticle with prominent SPM behavior existing even at normal environment. Definitely, I am also working with my groups as that is also part of this. My co-investigator to all this work is Manisha Patel, who is also working on this. So basically, this SPM is the prerequisite requirement for their future application. So basically, as it is clearly visible that SPM is unique, rare, but it is demand of the time that we have to achieve this at any case. So basically, then if we want to use in communication sector, then we do not require SPM. For that, we have to use a hard magnetic system. So dear friends, we have to check whether our application is in the communication sector, then we need a hard magnetic system. If our application is in the health sector or in storage sector, then we have to work in the soft magnetic system. Then we have also water treatment. For there, we have to use at the soft magnetic system. So out of the soft magnetic system or hard magnetic system, communication require hard magnetic system. Say for example, Government of India has received Rafale defense. I think we purchased last year Rafale fighter planes. So there, the communication technology they have used, that is basically they are using this a hard magnetic system which can work at ultra high frequency region, that is around X band or beyond that. So so for that we need a hard magnetic system. So dear friends, magnetic nanoparticle, it is of two types. One is soft magnetic system, and there is hard magnetic system. If we are in hard magnetic system, we do not require super para. But if we are in soft magnetic system, then we need a super para, because we want to use this as a super specialist kind of sensor which can detect any kind of any kind of magnetic pulse or magnetic impurity. So for that it is SPM. But if we want to use in communication, then we don't bother about that. Then we need a hysteresis loop of large area for the communication purposes. So it depends upon the application to application. Then if we talk about much beyond that, then whether it is ferrite system or garnet system or plumbite system. So in the present time, most of the research is in magnetic system moving towards very fast in the composite system, where people are working of chitosan as a polymer in the magnetic system, because chitosan is a suitable polymer which is compatible with the ferrite system. Then reduced graphene oxide is also very, very compatible with the ferrite system, soft ferrite system. So basically for use of these hybrid composite system of soft ferrite system, say for example nickel zinc magnetic nanoparticle coated with chitosan, then coated with the reduced graphene oxide, that is very, very useful for whether it is for immobilization or for treatment of hyperthermia, technology for the treatment of cancer, or there is also other kinds of soft magnetic system, that is lithium based ferrite, that is also very, very useful for the health sector. Then in the hard system we have a garnet system, or we have a hexaferrite whose corrosivity is very, very large. So in hexaferrite we are also actively working in collaboration with French people, and where we are using hard magnetic system from few hundred megahertz to 13.5 gigahertz. This machine was purchased in my department last year, but as you know, due to corona pandemic, because of lockdown, we are not in a position to to operate that machine. But definitely we have purchased that, and we are using hexaferrite of barium based hexaferrite, M type hexaferrite, or cobalt zinc type hexaferrite, which are very, very useful for ultra high frequency region. So basically whether it is in the communication or health sector, so it is basically M type or CO2Z hexaferrite, or in a soft side it is lithium based ferrite or nickel zinc ferrite, which I am presently working on, and there are results also, I think, which is already in my slides. I think I request please move slides further. Yeah, next. Yeah. So yeah, just this is the as I discussed, this is the SPM. So SPM is the unique state which I have mentioned. Next, please. Yeah, next. So here extreme left it is super para, and extreme right it is multi-domain. So extreme right it is a ordinary magnetic system, and extreme left it is SPM. So dear friends, if we want to use any kind of magnetic system, We have to achieve this SPM. No doubt it is tough task, but definitely if you are good researcher, if you are keen in understanding the magnetism, definitely you can achieve it. Next, please. Next. So as I mentioned, shape is also important. That is the beauty of this magnetic system. Shape is very, very important. As I mentioned, even in coronavirus, there are reports that it can change its variant when it enter in different environment. Say for example, I don't know, I can't say with, but there are reports. Say for example, if hot place, say for example, if you are in UP and somebody from UP carry coronavirus to enter in Uttarakhand, definitely there will be change in shape, size or surface because of change in the physical environment condition. So that is why, because you know that we are in the midway, because there is no clear data that it change different kinds of behavior when it enter from different region to different region. So definitely when we can observe in magnetic nanoparticle, it change its physical property. When we reduce the size, we change the shape, we change the surface. So if magnetic nanoparticle change its behavior when we change its shape, surface or size, so definitely coronavirus change its behavior because of definitely shape, size or surface. So how we can change shape, surface or size? Definitely somewhere physical environment is also responsible. In lab, how we can change its say for example size? So we can change either by by various kinds of solvent, by surfactant, by fuel. We add sometime fuel to reduce the size, or we can control the temperature, pressure. I think chairperson is the expert on that area. So definitely by changing the various kinds of physical parameter, so definitely we change the shape, surface or size. So if we change accordingly, its physical parameter or physical property changes. That is why we can somewhere correlate it with the COVID virus. So shape is also very important, surface is also very important, and size is also very important. Next, please. So this is Mosbor. Next, please. Next. Basically this is the SPM. So these are the results, as I mentioned, about nickel zinc or various kinds of soft magnetic systems. So these are soft frieds results. Next, please. So this is basically SPM. This is the exact morphology of SPM. So in SPM, there is no six line pattern as observed through Mosbor. So if your system is pure SPM, then it look like this. It has only doublet having some quadrupole moment and having isomer shift. That is the clear indication of the existence of SPM. Next, please. So this is the SPM through squid data. This is squid data. But this is in the controlled environment. It is in the presence of argon and in the presence of vacuum. So as I mentioned, there are reports also where people have reported that they can absorb SPM even in the even in ordinary environment also. Next, please. So again, this is SPM. This is magnetic nanoparticle coated with gold. So gold coated magnetic nanoparticle having SPM, and it can be used for the hyperthermia application, and we have used for the treatment of cancer for hyperthermia. So, data still is in the clinical trial. Next, please. So this is the approach of fabrication. So basically, this is the thermal decomposition method through which we can fabricate. We have fabricated these magnetic nanoparticle. Next, please. So this is the approach. Next. Next. So this is the XRD. having a spinal structure. So clear evidence. Next. So this is the exactly, just see shape. There is no agglomeration, because dear friends, if you want to use in health sector, your shape, your size and your morphology should be clear. There should not be any kind of agglomeration. They should be stable. They should be stable in aqueous medium and without any agglomeration. Next, please. So this is clear squid data. We are having clear high blocking temperature, which is suitable and close to 170 degrees Celsius. Next, please. So this is the theoretical calculation, AC susceptibility measurement, which we have put in theoretical modeling also. Next, please. So again, this is the gold coated magnetic nanoparticle. Next. So this is the HR10. Next, please. So this is SPM. Clear. This is SPM having corrosivity close to 0. So as I mentioned, dear friends, if you want to use any kind of application, we have to achieve the SPM. But anyhow, we have achieved in closed environment, that is in the presence of argon and vacuum. Next, please. So this is the Mosbor. So it is a, we have the Mosbor, there is clear indication from 6 line pattern to doublet, means shifting from bulk magnetic nanoparticle to single magnetic nanoparticle, or even at SPM having doublet. Next, please. Again SPM. Next. Next, please. This is another method, that is reverse micelle. So earlier method was thermal decomposition. This is reverse micelle. Next, please. So again, there is controlled surface size and shape is controlled. So reverse micelle, or this reverse micelle is also very, very important for if you want to fabricate excellent magnetic nanoparticle. But the negative part of this technique is yield is less. So if you want, if you need a high yield product, then I think you have to choose some other method. But if you want low yield product, then this method is very, very useful, where we can use surfactant. So by adding the surfactant, we can control the shape, size and morphology. And we can easily achieve SPM also. Next, please. So this is clearly super para kind of behavior. There is clear relaxation. Top one is simple collective magnetic excitation, but as we reduce the size, then there is change shifting, which there is clear transition from bulk magnetic excitation to super paramagnetic transition. So there is clear indication from the Mosbor spectroscopy, and simultaneously we have fitted through distribution function. So we fit it with distribution function also. So it is clearly matches with the XRD. Dear students also, if new student are there, research scholar, so basically you can correlate magnetic results with XRD. In XRD, if you want to correlate XRD of bulk and XRD of nano, so in nano XRD pattern is broad, but in bulk XRD pattern is sharp. So broadness means surface, reference. So same is the case in Mosbor distribution function also we fitted. So in bulk we have a broad Mosbor peak, but in bulk we have a sharp. So broadening means surface disorder. So dear friends, when we move from bulk to nano, so surface disorder increases. That is why there is broadening of peak at nano level. Next, please. Next. Yeah, so there is clearly, so this is in-field data. So we took the Mosbor in the presence of magnetic field at Indore, at IUAC Indore. Next, please. Next. So this is distribution function. Next. So this is in field. Next. Next. So this is all the parameter. Next. 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 So all these, the calculations. Next. 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 But this is interesting. At the center, this is the core. At the surface, this is the disorder. So we calculate the disorder thickness. How much is the disorder at the surface? So when we move from bulk to nano, how much is the disorder? We can calculate through Mossberg spectroscopy and field data. And we can also calculate by Langevin function. By Langevin function or using squid data. So we use squid data to fit Langevin function. Then we use the Mossberg data for cation distribution. So we calculate the surface disorder thickness. And dear friends, there was fair agreement between the thickness observed through squid data and the thickness observed through Mossberg. And I want to mention here that our group was the first with IUC people that we calculate this surface disorder by using Mossberg spectroscopy in accordance with the, in coherence with the squid data. Next, please. So again, this is squid data. Next. Next, this is the Langevin function, as I mentioned. So we calculate the theoretical calculation also. Next, please. So we calculate this Langevin function. Next. I think you are aware of Langevin function. Master degree program students, research scholars may be aware of Langevin function. So we fit it. The interesting observation from these curve was magnetic system. It was very well. There was little bit, disagreement between theoretical modeling and the experimental calculation. Next, please. So again, all these there is next, please. So again, this is the so this is the basically, next please. So this is the basically model we apply. So we Vogel law, then Neal law. So we try to fit it. Next, please. So this is the Vogel law, and we found that in our observation, it was the Vogel law which was very well helpful. That is the spin glass transition. Next, please. So this is the AC susceptibility measurement. Next. So future physics about this magnetism, as I mentioned, dear friends, the dynamic spin fluctuation and spin reversal is very, very important about these nanoparticle. I think you may be aware of the surface frustration. Surface frustration means spin fluctuation is somewhere responsible for hindering the magnetic behavior of these magnetic nanoparticle. So basically, core versus surface contribution, as I mentioned, in hybrid system or in any kind of system, one is core and other is surface. So surface is coated sometime with gold nanoparticle, silver nanoparticle, with polymer or with reduced graphene. So accordingly, you can manipulate magnetic nanoparticle with various kinds of super specialty kinds of techniques by manipulating, by engineering with coated techniques, different kinds of lithography technique, other related kinds of methods. So basically, future is in magnetism is about two important area. One is the hybrid system, as I discussed, and other is the core shell. So core shell is very, very important. At the core, you have a strong magnetic system, but at the shell, you have a surface spin frustration. So definitely understanding of magnetism at the surface, spin understanding, spin fluctuation, spin frustration, the kind of physics exist at surface, that is very, very important. So for that, we need a theoretical skilled manpower to understand the magnetism at surface level. Next, please. So GMR effect is also very important. So for that, this for GMR effect, as you know, spintronics is the core area. So spintronics is the future material or even present. Few circuits are based upon spintronics. So spintronics is also very, very interesting field in the future to come. Next, please. So basically, this is the kind of, as I mentioned, so earlier results was soft magnetic system, and this is the hard magnetic system used for, as I mentioned, in Rafale jet fighter, this, communication equipment which is installed on that is, French base. So basically, they are using hard magnetic system for it. So this is also the area which is very, very useful for, communication area. Next, please. So we are also working on this. So these are the results. So at the bottom, it is the imaginary part, and on the top, it is the real part. Dear friends, one thing is very, very important. If you want to use any kinds of hard magnetic system in communication, interesting part is your real permittivity and permeability should be high. That should be greater than 2. But imaginary, that is imaginary or loss, that should be close to 0. But in our struggle, we have controlled electric part. Permittivity, we are okay. Our permittivity, imaginary part is 0 and real part is greater than 2. But permeability, we are still struggling. We can't control, we are not able to control the imaginary part of permeability. Still, we are struggling there. But anyhow, we have purchased this machine. So definitely, in times to come, we will definitely control the permeability also close to 0. So this is also interesting area. Next, please. Again, as I mentioned, so we are still struggling with the permeability. Next, please. So this is the hyperthermia study which we have used. So we fabricate the iron-based nanoparticle coated with gold, or so we have used this for hyperthermia, and where we found that it can be very, very useful for the treatment of cancer cell. But as I mentioned, cancer cell is not specific; it is of different kinds. So this kinds of study is for limited kind of cancer cell, but still other kinds of cancer cell, still there are clinical trials going on in magnetic nanoparticles also. Next, please. So with these words, I think this is new. This is the other part of my talk, but I think I leave here with the remarks that, as I my today's talk was, I want to brief it in the way that if you are working in the material science, or you are working in the nanomaterial, or you are working in the magnetic nanomaterial. So at the present time, this is lesson to all of us because of this COVID pandemic. So I think we have to work in the front area where we can fabricate, various kinds of nanoparticle so that it can be useful for various kinds of application. So my message to new researcher is, please fabricate excellent kinds of nanoparticle so that it can be useful for specific application. So with these words, I am thankful to all the all the participants, all the organizer for listening my talk, and thanks once again my friends and my respected chairperson for and the organizer for giving me the opportunity. And I want to mention one thing. Manish is aware of that, chairperson. I want to especially mention before you, sir. I was day before yesterday at Haridwar, because during this time, actually 10 days before, I lost my brother who was for me like father. So I reached yesterday evening at my village. I am right now in village. So, but as you know, I can understand. It is all our joint responsibility that we have to do our karma, whether it is academic karma or domestic karma, we have to perform our duty. So with these words, I stop my talk here. Thank you very much once again for listening my talk. Thank you.
Thank you, Professor Singh, and I'm very sorry to listen to that your brother
Sir.
no more.
Sir.
May
Hello,
God-
sir. Hello, sir.
Thank you.
Hello,
Thank you,
sir. Hello, sir. Thank you for your very nice talk. I have one doubt, sir.
Oh,
Just
boliye,
please,
boliye.
please listen. I'll come to you. I'll come to
Sir,
you.
what is the effect of external parameters like temperature on?
May I know who is speaking? Please tell your name first. Hello. May I know who is asking the question? Please.
Yes,
Please tell
muted
your name.
himself.
Please tell your name. Hello.
He's muted now.
Okay. Thank you, Professor Singh. It was really
Yes.
very nice to listen to you, and but really sorry to listen that your brother is no more. Fine.
Hello, sir. Hello, sir.
Okay. Please tell your name
Hello,
first.
Myself, Ningapavati.
Okay.
Sir, I have one more doubt, sir.
Okay.
Right, right.
Ask.
Sir, what is the effect of external parameters like temperature on magnetic properties of material at nanoscale?
Oh, yes, yes. This is good question. Through, changing the temperature, you can control the, you can control the size surface. You can definitely control.
Sir, can you explain in detail? Sir, how can it can be controlled?
Yeah, by controlling, as you know, this saturation magnetization, it is dependent on, basically the size of the nanoparticle. Through changing the size of the nanoparticle, you can change the saturation magnetization. So saturation magnetization you can control with temperature. At high temperature, saturation sometime increases, but at some temperature it decreases. So it is basically optimization. You have to optimize the temperature. Through temperature, dear, you control the saturation magnetization. Through controlling the saturation magnetization, you control the size.
Right.
Okay. Thank you, sir. Thank you, sir.
Any other question, please? कहीं और से कोई क्वेश्चन है हमारे लोगों से?
Hello.
Yeah, please.
Yes, yes.
Hello. Good afternoon, sir. This is Pooja Rawat from Department of Physics, HNB Garhwal University.
Yes. Yeah, Pooja ji, boliye.
Yes, sir. Thank you for the informative talk. Sir,
Thank you.
I would like to ask, how does the broadening of peaks occur in case of nanoparticles in XRD?
Oh, as I mentioned, it is the surface disorder. It is the surface disorder. It is the, as you know, if surface is more than volume, it is the broadening. It is basically surface disorder.
Okay, sir.
In bulk, surface disorder is less. That is why peak is sharp.
Okay, thank you, sir.
Okay.
Any other question, please? और कोई लग नहीं रहा?
Dr. Sab, with the end, your visit to Shimla is due, but my promise was with you at Srinagar, but as you know, after some time we are passing with the COVID.
Yes,
so
that's what happened. Na? We met in November 18, I think. Na? November 19. Sorry. November 19.
Yeah.
And then after 2-3 months, it was a lockdown. And my visit is
definitely
pending. Yes,
it will be privilege for me to invite you in the department.
Certainly, I'll visit once this Corona thing goes. I'll certainly visit Shimla, sir. है ना? मैं आऊँगा जरूर आऊँगा सिंह साहब. अच्छा एक क्वेरी थी मेरी. है ना? एक क्वेरी क्या है कि सपोज आपके पास जो मैग्नेटिक डोमेन्स हैं, if they align somehow, you are not knowing them, you are not trying to align them, but somehow they get aligned. आपके टेम्परेचर से या कुछ है ना, सपोज दे गेट अलाइंड, देन इन दैट केस इट विल बिहेव लाइक अ सिंगल डोमेन,
या
है ना. तो फिर आपका जो ये मैग्नेटिक उसका कैरेक्टरिस्टिक्स है वो तो चेंज हो जाएगा, ड्रास्टिक चेंज हो जाएगा। तो कैसे पता करेंगे आप किसके अलाइनमेंट नहीं हुआ है, आप नहीं चाहते कि अलाइन हो, और समाव अगर ये हो गया, सारे डोमेन अलाइन हो गए, तो कैसे पता करें आप?
डॉक्टर साहब उसके लिए ना, हाँ यस, यू कैन टेस्ट इट बाय मैग्नेटिक पोलिंग। एक टेक्निक होती है सर मैग्नेटिक पोलिंग, आप एक्सटर्नल मैग्नेटिक फील्ड करके उसको अलाइन कर सकते हैं, उससे आप ऑप्टिमाइज कर सकते हैं कि व्हाट इज द इफेक्ट ऑफ अलाइनमेंट।
वो तो आपने किया, लेकिन आपका तो मेटल खराब हो गया।
हाँ, ऑल ऑफ दैट इज व्हाई डॉक्टर साहब ये जो एसपीएम है, दैट इज व्हाई आई मेंशन अगेन एंड दिस इज वेरी यूनिक। और ये इतनी यूनिक है सर कि एब्सेंस में ये कुछ नहीं शो करता, ये इतनी यूनिक स्टेट है, एब्सेंस में जीरो है। जैसे इवन माइन्यूट इवन फ्लक्चुएशन होगी मैग्नेटिक, ये इमीडिएटली सेंस कर लेता है। और मैं इसका एग्जांपल देता हूं डॉक्टर साहब, आपने अच्छा रेज किया, हमारा जो ब्लड है, हमारा जो खून है, इट इज ऑल्सो मैग्नेटिक,
ऑफ कोर्स,
but its susceptibility is very very small. So if you want to sense magnetism of blood, you need that kind, जो आपने पॉइंट आउट किया, वो अलाइनमेंट आपको सुप्रीम बनानी पड़ेगी, तब आप उसको सेंस करते हैं।
वो कंट्रोल में होना चाहिए आपके।
हाँ, यस यस
अलाइनमेंट शुड बी इन योर हैंड, योर कंट्रोल। नहीं तो फिर तो सब जो बना वो पता ही नहीं चला क्या बना।
यस सर, बिल्कुल, डेफिनेटली।
एक मैं जरा कोविड-19 पे थोड़ा सा फंडा क्लियर करो।
हाँ जी,
अभी आपने बोला था कि ये उत्तर प्रदेश से आया, उत्तराखंड में जाकर के उसका जो है वेरिएंट चेंज हो गया।
मैं आपको एक्सपीरियंस, मेरा यहाँ एक्सपीरियंस है।
पहले मुझे सुनिए, है ना?
हाँ जी,
मैं बताता हूँ। ये कोविड-19 जो वायरस है, ये आरएनए बेस्ड है बेसिकली। हमारे पास होता है ना डीएनए और आरएनए, तो मॉलिक्यूल्स है हमारे पास, जेनेटिक होते हैं, इसी पे लाइफ चलती है ना? दिस इज नॉट डीएनए बेस्ड वायरस, ये जो है आरएनए बेस्ड है। और आरएनए बेस्ड सिंगल सेल होता है, आप भी जानते हैं, मैं भी जानता, सभी जानते हैं। डीएनए जो है मल्टीपल सेल होता है। अच्छा, और आरएनए सिंगल सेल होने की वजह से, जैसे अमीबा पढ़ते थे ना हम हाई स्कूल बायोलॉजी में, है ना, सिंगल सेल, तो उसकी क्या क्वालिटी होती है, वो अपने को शेप चेंज करता है, जिसको हम आजकल वेरिएंट बोल रहे हैं, है ना? ठीक है। शेप चेंज इसलिए करता है, दैट इज ओपन स्ट्रक्चर बेसिकली, बीइंग ए सिंगल सेल होने की वजह से ओपन स्ट्रक्चर है, तो ये चेंज करता शेप, ये उसकी अपनी कैरेक्टरिस्टिक्स है। जबकि डीएनए शेप नहीं चेंज करता है। डीएनए जब तक उसको कुछ डालेंगे नहीं, तब तक शेप चेंज नहीं करेगा। तो डीएनए जितने भी वायरसेस हैं, वो कभी शेप चेंज नहीं करते, उसमें वेरिएंट नहीं आते। लेकिन आरएनए बेस्ड कोविड-19 आरएनए बेस्ड है, इसलिए शेप चेंज होता है, जिसको वेरिएंट बोलते हैं। वेरिएंट चेंज होता है क्योंकि इसके ओपनिंग्स है। अब प्रॉब्लम कहाँ है? प्रॉब्लम ये है कि वो चेंज अपने आप होता है, डजंट गो विद द ज्योग्राफिकल लोकेशन और देश और कलर, और उसमें नहीं होता है। ये उत्तराखंड और यूपी का मामला नहीं है ये। अच्छा, जो आजकल बोलते हैं ना कि हम कि इंडियन वेरिएंट है या अफ्रीकन वेरिएंट है, दैट इज आल्सो वेरी रॉन्ग कॉन्सेप्ट। ये कोई भी ऐसा नहीं हो सकता इंडियन वेरिएंट है, इंडिया में मिला तो इंडिया में 10 मिल गए आजकल, हाँ जी, इंडिया में 20 मिल गए या 5 मिल गए या 2 मिल गए। इट इज पॉसिबल विद ओनली विद दैट आरएनए सेल, क्योंकि ये उसकी कैरेक्टरिस्टिक्स है। हाँ, इसका एक फायदा क्या था, आरएनए होने की वजह से, सिंगल सेल होने की वजह से इसकी वैक्सीन 10 महीने में निकल गई। अगर ये डीएनए बेस्ड होता तो हो सकता है वैक्सीन आने में शायद 2 साल लगता। राइट। आरएनए बेस्ड होने से एक फायदा तो ये हुआ कि हमें वैक्सीन जल्दी मिल गई, रिसर्च जल्दी हो गई। नुकसान ये हुआ कि वी हैव मल्टीपल वेरिएंट, लेकिन क्योंकि वो बेस सेल एक ही है, फायदा क्या है कि जो वैक्सीन अभी हमने, चाहे कोवैक्सीन है, चाहे कोविशील्ड है, चाहे कोई और वैक्सीन है, इट विल वर्क फॉर ऑल द वेरिएंट्स बिकॉज द मेन जो सेल है वो एक ही है। तो ये प्लस पॉइंट बताना चाह रहा था।
मुझे नहीं था सर, ये तो दिस वाज माय असम्पशन। एक्चुअली हुआ क्या,
ऐसा मैं, आपने उत्तराखंड नहीं बोला तो मैं चुप मार जाता, आपने उत्तराखंड बोला,
एक्चुअली इन शिमला में हमने देखा सर, एक वो बाहर से जो आने के बाद स्प्रेड एकदम हुआ, और जो लोकल में, बट आई सजेस्ट यू सर, डॉक्टर साहब, मैं आपको सजेस्ट दूंगा कि आप अपना ये कोविड के ऊपर थोड़ा सा, क्योंकि आपका आरएनए बेस का इतना एक्सपीरियंस है,
ऐसा ना, मैंने लिबर्टी ली, यहाँ पे मेरे सभी लोग अपने घर के हैं, तो मैंने लिबर्टी ली बोलने की। अदरवाइज आई एम नॉट बायोलॉजिस्ट, मैं तो भाई फिजिक्स वाला आदमी हूँ, बायोलॉजिस्ट तो हूँ नहीं। पर फिर भी जो मैंने इंफॉर्मेशन आप लोगों को दी, इट इज 101% करेक्ट। कारण ये है, और इसीलिए हम सक्सेसफुल भी हुए इसके वैक्सीन लेने में। आने में। आप देखें नहीं हमारे बाकी जैसे उसका कई सारे और जो वैक्सीन थे उसको आने में 2-2, 3-3, 4-4 साल लग गए थे। वैक्सीन आने में बहुत टाइम लगता है, इसमें 10 महीने में वैक्सीन मार्केट में आ गई। Just because of this, it is RNA based. RNA based में आपके पास फ्लेक्सिबिलिटी थी, यू कैन वर्क, आप उससे काम कर सकते थे। डीएनए में बहुत मुश्किल होता है, इट इज टोटल क्लोज सिस्टम। डीएनए जो है क्लोज सिस्टम है, तो ये प्रकृति ने हमको प्लस पॉइंट भी दिया, नेगेटिव पॉइंट भी दिया।
थैंक यू
है ना?
थैंक यू
सो मच सिंह।
अच्छा ये बताइए आप अभी बैठे कहाँ हैं, उत्तराखंड में कि आप अभी इंदौर?
मैं इंदौर में ही हूँ, मैं पिछले 1.5 साल से इंदौर में फंसा हुआ हूँ।
चलो ठीक है सर, थैंक यू डॉक्टर साहब, टेक केयर डॉक्टर साहब, टेक केयर।
आप लोगों का सबकी दुआ रहेगी, सब ठीक रहेगा। थैंक यू सो मच फॉर योर टॉक।
थैंक यू
Manish, now you can take over.
Thank you so much, sir, for sharing your research work with us. And this information is going to be really helpful to cope up with the current situation of COVID crisis. Now, hereby, we will start our third session. And for this, I will request Professor R.C. Ramola, sir, and Professor Sib Krishna Ghoshal, sir, to please chair the session. Thank you, sir.
Thank you, Pooja. And a very good morning to all of you. I think it's still morning.
In this regard, I have an information. Prof.Sib Krishna Ghoshal have an important meeting with the Vice Chancellor in their university for the continuous increasing cases of COVID. So he apologized me to chair the session with Ramola sir. So Ramola sir, you please chair the whole session.
Okay, it's not a problem. Thank you very much for this information. But I would like to welcome all of you, of course, certainly because Professor Ghoshal was also a co-chair of this session. So on behalf of me and Professor Ghoshal, I would like to welcome you all to this third technical session of this seminar. And in the morning, you had two very informative keynote address, I will say, very informative keynote address from Professor Ghoshal and then from Professor Mahavir Singh. And now we are coming to the third session with the 2 invited talks and 3 contributed talks. And I would like to share here that the invited talk is of 30 minutes. So I'd like to request all the speakers to keep the time or keep their talk within 25 minutes so that we can have 5 minutes for the discussion. And the contributed talk are of 10 minutes. So we'll divide it at 8 plus 2, 8 minutes for the presentation and 2 minutes for the discussion or to answer any questions. So with this information, I would like to start